To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.
Hello and welcome. Today we have the honor of talking for a second time to Professor Tim Maudlin, this time about his proposal for a new theory of space and time, and perhaps a new theory of everything, which he refers to as full discrete geometry. Feel free to use the timestamp in the video description if you want to jump directly to Professor Maudlin's presentation. I don't recommend that, however, because what I'm about to say is an important part of the message. Professor Maudlin is one of the most widely admired academics, maybe the most, working at the intersection of physics and philosophy. The main reason for his widespread appeal, I think, is the clarity of his thinking and his realistic approach to understanding the world as the world is presented to us, which is one of his favorite expressions. I think his straightforward, no-nonsense approach is what people appreciate about him the most. I'm going to ask you to listen to his presentation on discrete geometry and to my presentation on the implications of discrete geometry in the same spirit. In other words, listen with the ears of somebody who wants to understand the world as it is presented to us, the world we experience when we open our eyes. Needless to say, humans are never going to agree about matters of interpretation, just as Maudlin and I do not agree here, even if we're talking about well-established science. So this begs the question, on a planet full of splintering ideologies and nuclear weapons, how are we ever going to keep our differences of opinion from destroying us? This question to me is fundamentally a management question, and that's what motivates my work in this space. There are reasons to believe that Maudlin might be on the right track with discrete geometry, but not quite right when it comes to understanding its full implications for the world as the world is presented to us. According to Maudlin, nature has no goals, and the future is irrelevant to the present, despite the fact that since the beginning of time, this is exactly how the world has presented itself to us as goal-oriented beings, and despite the fact that many top research teams are doing actual lab experiments and actual science founded precisely on this idea. In fact, we've talked to several of these researchers on this channel. Listen to my exchange with internationally renowned biologist Michael Levin and his call for an end to teleophobia in biology. Or listen to my talk with theoretical neuroscientist Carl Friston on the free energy principle. Or with pioneering physicist Vitaly Vanchurin on understanding the world as a neural network. Or with Eliyahu Cohen on quantum computing with the two-state vector formalism. All of these people and many more are making actual, tangible scientific progress using ideas that emerge potentially from discrete geometry. If these claims are not enough to make you pause, stand by for my talk with Fields medalist Michael Friedman, who not only won the prestigious Fields Medal in mathematics, but is currently leading Microsoft's quantum computing division. Unlike Maudlin's understandable first impression, we're not talking about pie-in-the-sky mystical thinking. This is actual work and actual science taking place at the world's leading research centers, and you're watching it unfold in real time. ASIM is happy to be at the forefront in this regard, and I hope you'll follow along as we continue to make strides. Despite our differences, I feel privileged to have talked to Professor Maudlin, and I'm grateful for his time. He has been a consummate gentleman and a great person, and I look forward to the possibility of taking a deep technical dive into his second volume on full discrete geometry as soon as it's published. Please see the video description for Professor Maudlin's bio, for all of the relevant links, and for the timestamp, because today's exchange is longer than usual. Thanks for your interest and support. Hello and welcome to A Theory of Everything. I'm Luis Razo, the director of ASIM and host of this channel. Today we have the honor of talking a second time to Professor Maudlin. Professor, thanks so much for taking the time to talk again. It's very generous of you.
Sure, glad to.
So as agreed, we're going to proceed as follows. To kick the discussion off, Professor Maudlin will give a presentation on what a clear and well-defined, formulated physical theory should provide. I will follow up with a presentation that builds on Maudlin's ideas and his proposal for a new mathematical approach to physics that he calls full discrete geometry. I don't think the full import of Professor Maudlin's work has been appreciated, and I hope to open some eyes today in that regard. So, Professor, before I turn the floor over to you, I'd like to anchor our discussion. You have this idea of looking at the world, analyzing the world as it is presented to us. And I think this is so profound. I think this is one of the reasons that you are admired so much. So I'd like to anchor this discussion with the world that's presented to us today as a world that's at a non-zero risk of self-destruction. So we're going to be talking about physics and math, which seems unrelated to the human predicament as a whole, but it's not unrelated. At least that's what I'm going to argue. And I'm going to ask that we keep this important background reality in mind. I think this can and should be, for every serious thinker, an important factor, important background to keep in mind as far as I'm concerned. So I hope that seems reasonable, Professor, even if it's a little unorthodox. So with that said, Professor, I'd like to turn the floor over to you, and we're all ears.
Okay, so I think I just want to begin with some very high level discussion, particularly of physics. So the connection of this to political and climate change and so on, which maybe you have in mind. I guess we'll see where that goes. But let me just start with physics and make some very simple points that I don't think have been quite appreciated enough. So physics, like biology, like chemistry, like even economics and so on, is supposed to be an empirical science, which means that we are able to test or check our theories, as one would say, against experience or against observation. And that if you don't do that properly, you're not engaged in any kind of serious empirical inquiry. And that raises the question of how exactly the world described by a scientific theory is supposed to make contact with the world, as you say, presented to us, what Wilfrid Sellars, the philosopher Wilfrid Sellars, called the manifest image of the world, which is more or less the world as it presents itself to you when you open your eyes and just look around, which means nothing about the microscopic structure of the world is part of the manifest image, because it's microscopic, and by definition we can't see what it is, so our only access to it has to be sort of theoretical. Now, I mean, there's a very simple point to be made here, which is that although when we talk about empirical data and observation and experience, that leads people quite obviously to think about consciousness and awareness and human awareness of the world, that at least in the case of physics, and really in any other science, no one has ever made or needed to make or used a direct connection between the postulates of the science and actual conscious experience. So if you think of sort of Newton has an entire physical theory, and that physical theory has lots of consequences about how planets will orbit and how bodies will fall and so on. But that theory, as Newton presented it, has exactly no consequences about anybody's experience or consciousness or awareness of anything, right? I mean, how could it? The conscious awareness arises somehow through our brains. Newton didn't have any theory of how our brains work, much less he didn't solve the mind-body problem. And so just that simple observation tells you that the way a theory makes contact with what we call observation or experience is not really via consciousness. So what is it via? Well, it's usually via what we think of as the observable features of macroscopic objects, of cannonballs and planets and so on. We think we reliably know certain things about how they move, particularly about their shapes and locations and motions. And then you can easily see how a physical theory could make predictions about that. And particularly if the theory postulates things at microscopic scale, like atoms, and you say, oh, well, the cannonball is just a collection of atoms, then the motion of the atoms determines the motion of the cannonball in a very simple way, an obvious way, and then you can see how the theory can make these sorts of predictions. So my main point here is that a well-articulated physical theory that we can understand both in itself and understand its relation to the world we live in, it has the following features. So it should postulate in explicit detail a space-time arena in which things take place. And that can have different kinds of structures. I mean, Newton postulated one very explicitly. Einstein replaced that in special relativity with another one, and then later replaced that in general relativity with yet another one with a slightly different structure. So we have space and time, that their structure that needs to be postulated. Then there should be some things in space and time. I mean, if you don't have any things in moving around, then it's not quite clear what good it does you to have it. And among those things are what John Bell, the physicist John Bell, called local beables, or just things that exist locally, right? Things that exist in some small region of space and time. He gives, as an example of something that's not a local beable, the total energy of the universe, right? That's not something that lives in some little region. But things like atoms and maybe electromagnetic fields and so on, maybe strings in string theory, which I understand you have some interest in, you can think of as things that are in space and time and moving in some way in space and time. So a theory should make a clear postulate of those sorts of things. And then the third thing the theory may have is further things that are needed to articulate the dynamics that are postulated in order to make sense or make predictions about how these things move. And those things may or may not be observable in any direct way. Electromagnetic fields, for example, are not observable directly. We only know they're there because, according to the theory, they in turn make charged matter move, right? And then we can see the motion of the matter. In quantum theory, we have the wave function or the quantum state that's postulated by all these theories. It's not directly observable. Why do we postulate it? Well, one way is to say because it's there to explain or account for how something else behaves. And they're clear. I think the clearest accounts of quantum theory are like that. And so you have these kind of three pieces that have to fit together in a coherent way. Now, the latter thing you were talking about space and time, is, as I said, one of these pieces is a kind of space-time structure, and it ought to, at macroscopic scale, if I kind of, squint at it and, ignore the fine details of it, it ought to sort of look like the world we think we live in. That is a three-dimensional space that somehow, with time going forward, it might have very different microscopic structure. In string theory, for example, usually the idea is that 4 space-time dimensions just isn't enough to do the theory, so they add more dimensions, go up to 10 or 11, and if you say, well, why aren't I aware of these other dimensions? Well, they're very tiny, they're compactified, they're like little circles, they're curled up at a very tiny scale, and so you can't directly see them, but they need to be there in order for the theory to make mathematical sense. So the thing I've been working on for some time now is investigating the possibility that space and time at a fundamental level are discrete and not continuous. Because the assumption of Newtonian mechanics, of Maxwellian electrodynamics, of special relativity, of general relativity, and generally of quantum theory as they've been developed, all depended upon thinking of space and time as continua, as infinitely divisible. And that leads to a certain set of mathematical constructs that you use to describe it. But you can imagine that at some very tiny scale, that's just not right, that you can't always take any 2 points and find another point between them and another point between them and another point between them and so on forever. So you might get down to a basic level where the points are countable, where in a continuum, for example, a point never has a nearest neighbor, because no matter how close any other point is, you can find one even closer. But in a discrete structure, you can talk about the immediately adjacent ones and so on. So I've been working on that for some time, and have some, what to me, rather surprising and interesting results, which if you want, I can go into a little bit of detail about. But right now it's kind of your call, how far you want me to get into
No,
this.
absolutely. Yes, please describe it.
Okay,
I think it's
so,
very relevant and interesting.
Sure. I mean, and let me just say that for people who would be unaware of any of this, other people have thought of this, not an original idea that space and time are somehow discrete. And in fact, it goes back to antiquity. But the way I've implemented, as far as I know, is different than the way anybody else has. So one might say, there's a particular thing people may have heard of called causal set theory. And the picture there is that space and time, instead of being continuous, are these individual points, events, that are then sort of connected by lines. So you get a kind of tinker toy, you might think, structure that's made up just of the points and the lines. And from that, you try and understand a large scale structure. This thing I've developed, which I call full discrete geometry, is full because it not only has, it has atomic elements of every dimension up to the size of the space. So in a two-dimensional space, it has zero-dimensional atomic elements, which you can think of as points, and one-dimensional atomic elements, which you can think of as atomic lines, which are not made of points. They have points as endpoints. They're bounded by points, but they're not constructed out of points. And then there are two-dimensional atomic elements, which you can think of as atomic surfaces. And if it's a three-dimensional space, there are three-dimensional atomic elements, which you can think of as atomic solids or atomic volumes. So that's a very general idea. That's just the idea of having atomic elements of all the different dimensionalities. Then you have to decide what their structure is. And here I'm also doing something that's a bit different than what most people look at. So one thing that has been investigated rather extensively is called the theory of simplexes. And the simplex is the simplest geometrical object of a given dimensionality. So again, a zero-dimensional simplex is a point, okay? A one-dimensional simplex is just a line with two endpoints. That's the same. A three-dimensional simplex is the simplest two-dimensional thing, which is a triangle. So you have 3 points, and you imagine this two-dimensional triangle that they bound. And then in 3 dimensions, you go up to 4 points and you have a tetrahedron and so on. So you have n-dimensional simplexes, and you can put these simplexes together and build things up. That's not what I'm doing. And this is one branch point where I think it just leads to different results than other people have. The idea that I've been following is sort of one that was suggested already by Euclid, who said a point is an object with no dimensions. And if you take a point and, as it were, move it, it traces out a line which has one dimension, the direction you moved it, if you will. And then if you take the whole line and move it orthogonally or in some other direction, that traces out a quadrilateral, which is a kind of two-dimensional thing. And if you take the quadrilateral, think of it as a square, and move it in yet another dimension, you get a cube or a square-based solid that has 6 sides. So that's the way that I've developed this. And the thing you immediately see is that there's a geometry there, but you might look at it and say, but that just doesn't look like the geometry of the world we live in at all. So let me just, and so this raises a sort of puzzle, which I want to raise and then show a way to resolve it. So if you don't mind, you said I could, I'll share my screen.
No, absolutely. Thank you.
And hopefully I can find, here we go.
At some point, if you can connect it to the objections you have with beables, that would be interesting. Or maybe they're completely separate ideas or concepts.
Well, this is, I'm sorry, this is a new computer and I have to allow it to share. Okay, there we go. See if I can now share the screen. Yeah, good. The idea here is that space and time themselves should be among the beables, that they should be among the things that actually exist. Bell made up the word beable as a contrast to observable. Observables are supposed to be things you can, as it were, observe. And what Bell said is, look, there have to be things that are just there independently of being observed, because you get into if for no other reason, you get into a vicious regress if you say something doesn't exist until someone observes it. And then you say, but then the observer already has to exist. Well, maybe because some other observer observes the observer, and on and on and on. And that doesn't make any sense. So Bell said, observables have to be built somehow out of beables, out of things that are just there. And that's what in philosophy we call the ontology of the theory. That is what the theory postulates just to exist. And so in this picture I have, among the things that a physical theory should postulate is a spaciotemporal structure or space-time. Most physicists are aware of this. They've made some very unusual suggestions about the space-time structure. As I said, the string theorists added more dimensions than you think are there because they needed to make their theory mathematically coherent. The so-called holographic hypothesis that people talk about a lot these days is supposed to be a hypothesis that there's not as much space and time as you thought there was. The way, if you look at a holograph or a hologram, it looks 3-dimensional, but it's really only 2-dimensional. So you sort of lose a dimension. So I think any well-defined physical theory has to have some account of space and time. And the obvious thing to do is to postulate a certain geometry. So let me just explain this structure that's in front of you. So this is just for a 2-dimensional discrete space. It's made up of points, which are the intersections in this little grid in front of you. And some of them are marked out there. And these lines, these 1-dimensional elements, which are, as you would expect, the little lines there, each of which is bounded by 2 points. And the squares are the 2-dimensional elements, the 2 elements, and they're bounded, each one is bounded by 4 lines. And this thing has a kind of intrinsic geometry. Now, one of the advantages of doing things discretely rather than in a continuum is that in a discrete structure, you have counting measure. You can just count things. When you try to count points in a continuum, you just end up with infinity all the time. I mean, if you draw any line, no matter how long, it's got an infinite number of points. And so you can't really measure anything by counting. But in a discrete structure, you can just count things. And the natural geometry, what we might call the intrinsic geometry of this discrete structure, is often called taxicab geometry. Because if you say, well, how far is one point from another? The natural thought is, well, how many of these little 1-dimensional links do I have to pass through. If I start at one and I want to get to another, I have all these routes that I can get following on this grid. And a natural way to measure the length of one of these routes is to just count the number of jumps I have to make from a point to an adjacent point to an adjacent point. And it's called taxi cab geometry for the obvious reason that if this grid were the grid of the city streets and you got into a cab and you wanted to get from one point to another, the distance shown on the meter wouldn't be what we think of as the bird flies distance, but it would be the distance as you follow the roads. And so if you look at the point marked C at the center, I could define what would be the analog of a circle of unit of radius 3 in this geometry, which is the diamond that's indicated there, meaning that the shortest route from C to any of those points is of length 3. So I can go 3 out or 3 up, or to get to the other ones, 2 over and 1 up, or 1 over and 2 up, and so on. And you'll notice that this thing that kind of corresponds to a circle isn't a circle, it's a diamond, or it's itself a square. And that's very different than the geometry we take ourselves to live in. It's very different than Euclidean geometry. One easy way to see that that's true is that in Euclidean geometry, if I have a pair of circles, either they don't intersect at all, or they intersect at a single point if they're tangent, or they intersect at a pair of points, but that's it. They can't intersect at 3 points because 3 points determine a circle. So 2 different circles can't intersect 3 times. But if I imagine this analog of a circle around D and go out again 3 units, I would get another one of these diamond shapes, and it would intersect completely along that one edge that has 4 points in it. So even the way these things intersect with each other doesn't correspond to Euclidean geometry. So the intrinsic geometry looks very, very, very non-Euclidean. It obviously has preferred directions to it, the way Euclidean space doesn't, and so on. So,
Professor, so one of the points here, or the main point here, is that you are beginning from a non-traditional approach. It's non-Euclidean geometry.
Yeah, it's non-traditional, and you might say, okay, you've, as my friend Shelley Goldstein used to tell me, which is very useful, you've just defined something, but what is it, right? Why would anybody think this could correspond to the world we walk around in? Because the world we walk around in is pretty nearly Euclidean, right? I mean, Euclidean geometry does a very good job of making sense of the world we live in. And you're giving me a fundamental structure that's absolutely non-Euclidean in a very radical way, right?
So the question is, how do we get to the real world as it is presented to us?
That's right. That's a challenge for this, right? That's absolutely a challenge. And the interesting thing that I just want to show you, and I'm gonna show you one thing that's very clean and one thing that's not quite so clean, but hopefully it'll get the point across, is that there is a way, starting from this geometry, to get you to something that is approximately Euclidean. And the key is to add time. And this was a real surprise to me, that is, everything I've talked about so far is just space. But we live in a world that has both space and time, so I need to add some temporal structure. And I'm going to do that also in a discrete way. I'm not going to have continuous time. I'm going to have events, and then there'll be a set of immediately succeeding events or immediately preceding events with none in between. So again, you just have nearest neighbors in time. And if you start with this picture of spatial geometry, it's not at all clear how you add the time structure in. So let me just jump down here and do an even simpler case. So let's go down to a one-dimensional space. So what you have here at the bottom, these blue dots and the lines, that's a simple, discrete, one-dimensional space. So point, line, point, line, point, line, forever in both directions. And then I'm going to add a second copy of that immediately above it. And then I'm going to draw these arrows. And the arrows are temporal arrows. They represent succession in time. They are arrows because time, unlike space, has a direction. And so we distinguish earlier and later. And what I want to do now is connect these two layers with these arrows to explain which of these geometrical pieces immediately comes after which ones. So the simplest, one of the simplest things I can do is just do what's in this diagram, is make a copy and draw a single arrow up from each dot to one other dot and from each line to one other line. So each point would have one successor in time and so on. This corresponds in a certain way to the way Newton thought about space, absolute space persisting through time, because he thought points in absolute space remain through time. So you can pick out a point in space and then ask a second later, well, where is that point in space? And another second later, where is that point? So you could do that, but this structure would not be much good for physics if you make some very obvious requirements. For example, suppose you have particles and each particle is at one of these dots at every moment, and you restrict their motion to be continuous, meaning here you always go from a dot to an immediately succeeding one, or you follow the arrows, right? Well, in this structure, there just aren't enough arrows. I mean, in other words, if I start out with two particles that are right next to each other in the grid, then the next moment they'll still be next to each other, and the next moment they'll still be next to each other, and there'll be no motion, right? Nothing will change its relative position. That's not what we want. So I need for each of these points to have more than one successor in time. All right. I can go wild in the other direction and essentially draw an arrow from every point on one layer to every single point on the next layer. And this is the discrete version of something that we call neo-Newtonian spacetime, or sometimes Galilean spacetime. And now I certainly don't have the problem that two particles that are next to each other have to remain next to each other. I kind of have the opposite problem, that by following these arrows, two particles that are right next to each other at the next moment can be arbitrarily far apart from each other, right? Because they can go from any point to on one layer to any point on the next layer. And so there's no restrictions on the motions at all. And that seems wrong and certainly doesn't correspond to the way we think space and time work in the world we live in, which has a kind of relativistic structure. So I hope you get the idea. It's something very simple here about how am I going to put these arrows in? And one arrow coming out from each dot is too few, and an infinite number is too many. And the next simplest thing to do, which turns out to be actually quite effective, is, okay, how about two? Then we get this structure. And you'll notice that the spatial structure at the bottom gets shifted the next layer up, and then shifted back, and then shifted. And then from each point, essentially, you can either move right or left. So you have a binary choice at each moment. But now, two particles that start out next to each other at the bottom, well, they could stay next to each other. They could move apart, right? But they're limited to how fast they can move apart. So essentially, this structure already has something that corresponds to what we think of as a relativistic light cone in it. It looks, in fact, it looks very much like what a light cone would look like in a two-dimensional relativistic spacetime, in a two-dimensional Minkowski spacetime. So that is kind of what I call a minimal spacetime, because it's the fewest number of arrows that doesn't trivialize the whole thing. And that's it for one spatial dimension plus time, so 1 plus 1. Now, the thing I want to show you, which gets really interesting, well, before I do that, now, here's just a mathematical question I can ask. And again, because I can count, I can just cleanly answer this question. So take any 2 points, like A and B, or A and E, or whatever, And you can ask, all right, how many distinct paths connect those points? How many different ways are there to get from the one to the other following the arrows? Obviously, if I go from A too far off to the right or the left, the answer is 0. I just can't get there. There's one path that'll take me from A to D. That's the one that goes through B. But there are two paths that'll get me from A to E because I can go A, B, E, or A, C, E. So this is this quantity that's well defined, which I call path connectivity. And we can just count paths. Now, the way you count paths in this 1 + 1 structure is quite familiar. People have probably seen this. It's done by Pascal's triangle. So probably everybody knows this. You just start with 1 at the top, and then you get each entry on the table by adding the 2 entries above it, or 1 entry if there's only 1 entry above it. And you get this table, very easy to generate. And those numbers are counting, one thing they're doing is counting paths. So if you look at the number 15 at the bottom, it means there are 15 different distinct routes that will take you from the one at the top down to that point at the bottom. And you can run down one side and in, or this way, that way, or jiggle your way down. And you can do it 15 different ways. For the central one, there's 20 and so on. This is very well known. And so essentially Pascal's triangle is, one thing it does is counts path connectivity in the kind of structure I just showed you. Good. Now, let's move from the simple one-dimensional case to the two-dimensional case and do the same thing. So I have my two-dimensional grid. I have another copy of it above. And I've offset the copy above so that each dot below is centered at the center of a square above it. And then I've drawn from each dot below 4 arrows that go up to the 4 corners. And this is a kind of, again, minimal, non-trivial thing I can do. It gives me this kind of truss structure, and then I can repeat that, and I'll get a discrete space-time out of it. It, again, has a kind of light cone structure. If a particle always has to follow these arrows, it can't, it's restricted to lie within what really looks like an Egyptian pyramid kind of shape. Because the arrows are always restricting it by that means. And here's another picture of this space-time from the top. You see the solid dots are the upper layer, and the crosshatch dots are the lower layer. And from each dot, you have 4 arrows going out. So essentially 4 different directions you can go in. And then from there, 4, and from there, 4, and from there, 4, and so on. So again, that's a space-time. It has preferred directionality. It doesn't look at all Euclidean. The geometry, again, looks like taxi cab geometry if it has any. So let me just pause here. Is everything clear so far?
Yes.
Good. Okay, so if everything's clear, I'm now going to show you some magic, right? Some mathematical magic that really shocked me. I didn't expect this, okay? I didn't design it. I was just developing the simplest thing I could think of. And now I just want to show you a very interesting feature of it. So suppose I have this discrete structure. And again, I asked this question about path connectivity. If I have a point, and imagine a very big truss like this, I pick 2 points and I say, how many different paths connect these points? Well, to count, I'm going to do something like Pascal's triangle, but there's another thing, I'd never heard of it, but I found it, called Pascal's square base pyramid. So you imagine just piling blocks up on each other in this way, and doing the same thing as you did with Pascal's triangle, that is, you write a 1 in the top block, and then you just, for all the lower blocks, you just count the numbers that are in the 4 blocks above it, right? The 4 blocks that it touches above it, if there are 4, and you get this kind of pyramidal structure. And let me just go down and show you, if I cut through this, the fifth level down, this is what it would look like. That's what the numbers would look like. So this is level 5 of the pyramid. And if you just stare at that for a minute, you notice two things about it, and it's very easy to understand why it has this structure. One thing is along the 4 edges, the 1, 4, 6, 4, 1, well, that's just Pascal's triangle, right? So if we go back here, you see 1, 4, 6, 4, 1 down there at level 5. So the numbers along the edges are already familiar. They're just the Pascal numbers. And then the other thing you notice is that the interior numbers are just, the whole thing is a multiplication table. That is, you get any interior number just by multiplying the 2 edge numbers that come in and that intersect there. So, 24 is 6 times 4 and 36 is 6 times 6. So it's very easy to figure out what these path connectivity numbers look like. And it's if you think about it, it's kind of easy to see why it has this structure. Along the edges, it's Pascal's triangle, because to stay along the edge, you always have to move. Say, if I want to stay along, you might say the right edge, I always have to move to the right, but then I can either go up or down. And so again, I just have a binary choice at every layer, and so I just get a Pascal triangle. And the reason that it's a multiplication table is that the motion up and down and the motion right and left are independent of each other. So I can jiggle any way I want this way, and then jiggle independently any way I want in the orthogonal direction. And so I just multiply those possibilities together. Good. Now, if I make this really, really big, the numbers get big very, very fast, and very, very big when you start counting these paths. This is just combinatorics. And when these numbers get big, the Pascal numbers, the like 1, 4, 6, 4, 1, as you know, sort of starts to look like a bell curve. It starts to look like a normal distribution. It's not exactly one, but the more layers you have, the closer that distribution of numbers starts to look like a bell curve. And so we can use Stirling's approximation, which is an approximation for this Pascal's triangle or binomial distribution. And leaving out the details, the finer details of the approximation, if you just look at the bottom line here, it basically says that the numbers are proportional to e to the minus x squared. So what does that mean? Well, e is the base of the logarithms. The minus means you're doing 1 over. So as the number x squared gets big, this number gets small. And the x squared is sort of measuring the distance from the center. So it just says, I start at some height at the center, and then as I go out, it goes down, and this will form a standard bell curve. And the mathematical way that this approximation is written is what I have here. Now, it's approximation. It's going to break down in certain circumstances, but it's a pretty good thing. So we're going to use that e to the minus x squared with some constant out front to represent the connectivity numbers along the edges as I go very high up in levels in this structure. Now we're almost done. So in 2 dimensions, as I said, you have e to the minus x squared, which is giving me the distribution in the x direction. And you would have e to the minus y squared, which is giving me the distribution in the y direction. And to get the total number of paths, I just multiply those together. So that's about the connectivity. If you look at the middle line there, the connectivity is about some constant, e to the minus times e to the minus x squared times e to the minus y squared. And when I multiply like that, the exponents add. So that's e to the minus x squared plus y squared. Now, what is that little formula there telling you? It's telling you, and think of x and y as kind of Cartesian coordinates here on my grid. It's telling you that if you have 2 points, each point has coordinates x, y, so I've got x, y, say, and x prime, y prime for two different points, that if x squared plus y squared is about the same as x prime squared plus y prime squared, then the connectivities are the same. But the set of points given by x squared plus y squared equals a constant is a Euclidean circle. So if you just only pay attention to degrees of connectivity, circles emerge, Euclidean circles emerge. The preferential directionality disappears. In other words, if you could just squint at this discrete structure, but all you could see are the level surfaces of connectivity, the points that have about the same connectivity to this base, what you would see is sets of, when you cut this way, what you'd see is sets of Euclidean circles. Now, that goes a little wonky as you get far enough out toward the edges and the Stirling approximation breaks down. But where the Stirling approximation is good, you now get, in a very simple way, the emergence of Euclidean structure from a foundation that's as non-Euclidean as you could imagine.
Surprising.
Yeah, now I'm going to show you something even more surprising. This, again, I didn't design this. I just stumbled across it. And what I'm about to show you, and now I'm going to tell you something I've only realized in the last week. Okay, so this is new. What I'm going to show you something in 2+1 dimensions. It's not quite as good in 3+1. So this emergence of circles is going to be good in any number of dimensions. This very same arguments will give you the emergence of spheres, of Euclidean spheres in 3 dimensions, and so on. The thing I'm about to give you isn't quite so good. It works really great in 2+1 dimensions, but let me give it to you. So what I said was, now imagine you've got this grid. Imagine that, it's at a very, very, very fine scale. So you've got many, 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 many levels, and you blind yourself to everything except connectivity, and you cut it horizontally, then you get this circular structure. Let's cut it vertically instead of horizontally. So in other words, I'm going to cut this way. I'm going to pick a point, and there'll be certain connectivity to it. And then I'm going to look for the other points at later times that have the same connectivity. Not at the same time, but at later times. What kind of a shape do I get there? Well, in special relativity, what you have is the fundamental space-time structure is called Minkowski space-time. And from any given event, you have something called the proper time that's defined from that event to any other event in its future past light cone. And the levels, if I say, well, give me all the events that are, say, 1 second in proper time from here, that set will be a hyperbola. Okay, it'll satisfy this formula, delta t minus delta t squared minus delta x squared equals a constant. So it'll be a hyperbola. Right? So that hyperbola shape is characteristic of relativity in the same way that the circle is characteristic of Euclidean geometry, right? Now, there's not something quite as clean about this, but let me just give you some numbers here. So if I want to count the path connectivity, and this is now not using any approximations, the exact formula, combinatoric formula, for the number of paths, if I start here and go up n levels, and then if I move out in the x direction to the point x, and in the y direction to the point y, where the zeros are at the center, the number of paths is given by this formula. This is just the standard combinatoric formula. So let's just run some numbers. So let's imagine this structure I gave you, go up 800 levels and go to the center point, the point right above the one that I started, and calculate the path connectivity. So that's this number, 800, 800, and then 400, 400, 400, 400, that's n over 2. And that gives me this number, 3.5 times 10 to the 478. I told you the numbers get big, and they do, right? I've gone up 800 levels. I'm already, the number of distinct paths that connect me are, I need, a 1 followed by 478 zeros. So this is a big number, yeah? but just kind of remember that number, 3 and change times 10 to the 478. All right.
Okay.
Let's move up 10 levels to level 810 and ask, if I stay at the center, the path connectivity will have gone way up. But as I move off to the sides, it starts to go down again. And so let me say, how far along the x-axis do I have to go? How far do I have to move out to get back to this same level of connectivity of 10 to the 478, 3 times 10 to the 478? Well, you can just go, I mean, Wolfram calculator will actually calculate these numbers. It's amazing. I didn't think you could because they're so big, but it does. And you can just play around. And you can find easily, anybody can check this, that the nearest number I can get is I go out 75 units, okay, along the x-axis. And that gives me this number, which is 3.1 times 10 to the 478. So just about the same. So in order, so I started at 0, 0. I started at the center. I go up 10 levels, and then I have to go out 75 spots to get to the same path connectivity. All right. Now, I now have enough data to fit a hyperbola to that. So if I say the bottom of the hyperbola is here, and then I need the hyperbola to go through so it goes through 800, 0, 0, and it has to go through 810, 75, 0. I can now fit a hyperbola to that and now make predictions of or see where that hyperbola will intersect even higher levels. Now, before I do that, instead of going out along the x-axis, one thing I can do is go out along the diagonal. So I go out the same amount in the x and y directions, and again, find the point that's nearest times 3.5 times 10 to the 478th, and that's down here, and that turns out to be 53. I have to go 53 this way and 53 this way. And again, you notice that 75 squared is almost exactly 53 squared plus 53 squared, which is this telling me I'm getting these circles, right? Getting these circles at the level. But I now have these 2 points, one here and one at 800 and one at 810, enough data to fit a hyperbola to that. And now I'm going to go up all the way up to level 1000. So pretty far up, and use that hyperbola to make a prediction about where I'll find the same amount of path connectivity up at level 1000, right? And what do I find? Well, the first thing I've done here is just using the calculation for fitting the hyperbola, and that yields me a prediction 354.6, which rounds up to 355. And then I just plug that into my formula and look at the number, 3.3 times 10 to the 478. So I mean, that prediction, which I get out of using relativistic proper time structure, is almost exactly the same. So if I cut in the 2 + 1 dimensional case, if I cut this way and look at surfaces of equal connectivity, of level surfaces of connectivity, I get something that is very, very, very close to a relativistic hyperbola. And so you say, well, gee,
I found this on the web.
oh, sorry. You say, gee, if, and this is a big if, you need to fill it in. If the physics was sensitive to path connectivity, if what the physics kind of responds to is path connectivity, then even though I'm starting with this discrete structure that is as non-Euclidean and as non-relativistic as you can imagine, the connectivity structure in it that emerges is strictly Euclidean and very nearly relativistic.
Mm-hmm.
Now
interesting.
You one more step and you say, okay, that's a very interesting mathematical fact. Now, again, I have to say, and I've just figured this out in 3+1 dimensions, which is what we want, the fit isn't quite as good. The fit goes down a bit, but you still have a pretty good fit, but it's not as good. I mean, this fit is amazing. This just shocked me. I mean, I didn't fiddle around with this. I just plugged it into the calculator and saw what dropped out in front of me. Now you say, okay, that's very interesting. That's pure math. In order for this math to have any physical significance, I need a theory where path connectivity makes a difference, where counting these paths is somehow physically relevant. It wouldn't be, you think, in Newtonian physics. It wouldn't be in Maxwellian electrodynamics. But then you notice, gee, there's this theory called quantum theory.
Yeah, and the path integral approach.
And one way that you can present it mathematically is called using a path integral, where you take integrals over paths. Now, when you do that in a continuum, it's not even well defined because there are infinitely many paths, and in some sense, most of them are fractals, but people still talk about it this way. But here it's clean, right? You've got a finite number of paths, you can enumerate them. It looks like if something like a quantum theory that's where the dynamics is given in terms of path integrals is implemented in this structure, you would expect the result to look very relativistic, even though the fundamental space-time structure is completely unrelativistic. So,
and non-Euclidean.
And non-Euclidean. And you would expect something that looks pretty Euclidean, right? Even though the underlying structure is completely non-Euclidean. So to me, this is very intriguing, right? I mean, it's a long way from what I just said to implementing all of this and I don't want to oversell it. But on the other hand, the picture I gave you is very simple. It's, in a sense, the simplest non-trivial way of doing what I was set out to do. That's how I came to it. I didn't experiment with 36 different structures and then find one that did this. This was the only one I tried because it's the simplest one that's non-trivial. And what you find apparently falling out of it could be the basis of an explanation for why the world looks Euclidean and looks relativistic, even though the fundamental space-time structure is discrete, is not only discrete, it has preferred directionality, it has a preferred foliation in time. I mean, this is as non-relativistic and as non-Euclidean as you could imagine at a fundamental level, but at the level of path connectivity, what you get naturally emerging looks Euclidean and really Minkowskian, right? It looks sort of like the space-time of special relativity.
Very, very interesting. Talk about the connection to directionality and time. Would you? Can you?
I can, but it's so trivial. I can say it in a sentence, which is that.
Sure.
Of course, it's essential here for what I'm doing. Let me go back a second. It's essential here, if I look at this grid, that the time connect arrows have arrows on them, right? Why? Because if I just look at the spatial structure, let me go back to the pure space here. If I take any 2 points in that space, which has no directionality in it, and I ask how many paths connect any pair of points, the answer is always infinitely many. Because take even 2 points that are right next to each other, I can always take a path that goes way up here and around and curls around and then comes back, right? And I can go further away and come back. So path connectivity trivializes if you don't have directionality. The reason why the path connectivity can be counted whoops, I've gone too far now. The reason why the path connectivity can be counted here is because these time arrows they're arrows, and you have to follow them tail to head, right? And that reflects the obvious fact that time has a direction. Now, I know that any number of physicists and any number of philosophers will insist that no, time doesn't have a direction. And I don't think it makes any sense. I don't think any of the arguments people have put forward to that quite astonishing view that time doesn't have a direction hold any water at all. I don't think they make any sense if you look at them carefully. I think time has a direction, okay? The earlier, later relation is an asymmetric relation, and there's no corresponding spatial relation that's asymmetric, right? Space doesn't have a preferred directionality. Time does. So the relation to time direction is I put time direction in the beginning, and if I hadn't, I couldn't do any of this. If I took the arrows off those, then again, between any 2 points, there'd be infinitely many different ways to get your way from one to the other, right? The path connectivity would immediately go infinite if time was not directed. But time is directed. So, you know.
Certainly in our experience of it. Yeah, excellent. Can I ask you a question? What is the ontology here, which was your goal in the first place, right? Because any well-formulated theory must indicate the ontology. So the ontology here is discrete geometry.
That's right. That's part of it. As I said, I would say for any complete physical theory, and I certainly haven't given you a complete physical theory, it should have an account of space-time. It should have an account of the local physical beables, the physical things that as it were, are located at points here or on edges or whatever, and whatever else it needs, and then gives you a dynamics. And the dynamics is stated in terms of the space-time structure. It's specified in terms of the space-time structure. All I've given you is the space-time structure. Okay. And I've indicated why, of course, to complete a theory like this, you would now have to say, okay, what are the local beables? Maybe there are particles, maybe there are point particles. At any given moment, a point particle is at one of these dots, and then it moves to a temporally adjacent one, and then moves to a temporally adjacent one. Maybe there are things that are like the edges that are one-dimensional fundamental things. Maybe there are things like the faces, they're two-dimensional fundamental things, and they have a motion. All of that, what this does is it gives you a kind of spaciotemporal palette upon which you then would specify the further ontology of the theory and the dynamics. And what I've indicated is that the way the dynamics of the wave function is done in quantum theory seems intuitively to connect to what I've given you if you do it in a kind of path integral sort of way. But there would be a lot of work, much further work, to exactly try to translate standard quantum mechanics into this setting. And there are lots of decisions to make, just as there were decisions to make for this structure. There are any number of other kinds of discrete structures you could specify, right? And I have no reason to believe that there might be others that do just as well, or maybe even do better. As I said, this goes a little bit pear-shaped when I go up to 3 dimensions, not too bad. And if I'm, in an optimistic mood, I might say the way it goes pear-shaped could explain what's called the cosmological constant. Okay, I don't want to get into that. There are lots of resources here, right? The main thing I think of this is that it's kind of a proof of concept, that you can do things discretely, but more importantly, that starting from a discrete basis, you can get emergent in a very natural way things that correspond to the continuum geometry that have been used in physics, right? So you would get an explanation for why Euclidean geometry works as well as it does, even if the fundamental structure isn't Euclidean. You can get an explanation for why relativity works as well as it does, even if the fundamental structure isn't relativistic or isn't Lorentz invariant, as we would say. You can get Lorentz invariant structures to emerge in a very natural way. And so I think now, we talked about this a little, there are many technical advantages to doing things in a discrete way. One obvious one is you don't get singularities. So singularities arise when you're dealing in a continuum, because sometimes your functions grow without limit. They blow up to infinity. But in this structure, the natural way you do the math is you're always just adding finite numbers of finite things. And if you do that, nothing ever blows up. It can't. So you're safe from some of the main actual mathematical problems that have haunted quantum field theory from its beginning. As you try to do quantum field theory and you run across these singularities. And this, just people didn't know what to do with them, and they tried some mathematical tricks that don't seem all that justifiable, or they, as they say, put in cutoffs to make things mathematically tractable. But what you have here is you don't put in a cutoff. There, as it were, cutoffs are already there in the space-time structure, right? You don't add them. They're built in the very foundations of the thing. And so you just can't run into problems like singularities.
Excellent. Very, very interesting. So is this the subject matter of your first book on the physics of geometry, or is this the second book?
This is the second as yet non-published and non-finished, right? So I did a kind of conceptually similar thing in this first book called New Foundations for Physical Geometry, the Theory of Linear Structures. There I was looked into the standard way you do topology, which is well suited for continua, but not at all well suited for discrete structures. And I found a different way, a different conceptual foundation on which to base topology, rather than the open set, which is what's used in standard point set topology. And so I developed all of that, and I did all the math in that book. And my intention for the second volume was to use that and then translate, some physics into these terms, which would be a relatively straightforward thing. But then once I started writing, I got this idea that one nice thing of what I did in that book is that it applies not just in continua, but also in discrete spaces. And so I started thinking about discrete spaces. And then as I thought about discrete spaces, I developed this whole full discrete geometry. And now this has taken over the whole book, right? It's what was supposed to be a follow-up to the first volume is now a completely separate thing, which will not make much of any reference to the first volume, but it's going to lay out all of this full discrete geometry and hopefully get to the point of at least indicating how you could use it to do something like quantum theory, and why it would be good to do that, right? Why it gives you some advantages over what's standardly done.
What kind of time frame are you thinking about at this point for the second volume?
I mean, there's 6 chapters. The first 6 chapters, which are done, are just the spatial part. And given what I said here, you might say, why does it take you 6 chapters? And it's a long answer, but the short answer is standard physics, when you first learn it, is done using vector calculus. And what I was trying to do was think hard about the fundamental differential operators that are used in vector calculus and how to reproduce those in a discrete setting. And there are very interesting results from that. I mean, to me, extremely interesting. That's all space. Then that's all done. Then you start adding time, and I've basically gotten to here. But I haven't even finished the chapter laying out everything I just told you. I said one of the, looking at 3-dimensional, 3 + 1 dimensions, I only did that, in the last week. So I'm still working on that. I have ideas. I mean, there's a question of where you draw a line. I want to get far enough to indicate why this fits well with quantum theory, which I can do. The problem is, of course, as you do it, you always think, oh, maybe I can go a little further. Maybe I can go a little further. So I don't know when it'll be done. It's certainly taken me already 5 years longer than I thought it would take because I wasn't planning on doing any of this. And, I've been giving talks about this to get the ideas out, but there's so many choice points when you do something like this that it's a mistake to do it quickly, because often you'll just grab at something and then it takes you a while to realize, no, there's something better, or there's a different way to approach this. So I'm taking my time with it.
Sure. Well, you're developing something completely new. Fascinating. Congratulations. Well, I've been struck, as I mentioned earlier, by some of the parallels between a discrete line and some of the conceptual similarities to string theory. And of course, string theory is a very well-established approach to quantizing gravity and in terms of the number of adherents and its impact on other areas of physics and math is very promising. Mm-hmm. So if it's okay, I'd like to if you're done here, sure. I'd like to run through some of those similarities and then we can discuss them along with some interesting connections to time, which I think are again, I think they're super promising. So if it's okay, I'll share those.
Yeah, let me turn off my screen sharing if I can. I just have to figure out I'm somehow, oh, here we go, stop sharing. There we go.
Okay. So a couple of questions. The ontology here is, there is no ontology at this point, if I've understood your answer so far.
Right. What the material ontology, we might say, I have not put in yet, right? It would be easy. The way I'm going to do the quantum theory is the so-called pilot wave kind of picture, where you have point particles that move around in the continuum case. And here, if adding point particles is easy, they just are at these point locations and they always move along continuous, they follow the arrows. And then you need to give you need to give the dynamics of the wave function and the guidance, the way the wave function determines these motions. But I haven't talked about any of that yet. All I talked about was that the dynamics of the wave function itself is often done in a kind of path integral way, and you can see why that would lead to a kind of relativistic looking structure here.
So how would you characterize this as an interpretation of, it's not an interpretation of quantum mechanics.
No, I hate the word interpretation. I mean, one of my things I complain about all the time, it's a theory, right? It's a theory, yeah. Just a theory. It is not an interpretation of any presently existing thing. It's a new theory. As far as I know, nobody else has tried to develop something like this. It should return, at the end of the day, predictions that are very close to quantum mechanical standard predictions. Why? Because we know those predictions are really good, right? That's just a matter of it being empirically adequate. It better somehow allow us to make at least very similar, not necessarily identical predictions. In fact, my guess is that any theory built on this basis will diverge in small ways from standard theory, because even though you get something, say, that looks like Euclidean geometry emerging, it's never exactly Euclidean. They're always at a small level, at a sort of epsilon level, divergences. And once you have a theory in front of you, you can ask, okay, where might those divergences show up? Maybe I can go into a lab. Maybe I can do some cosmological observation, right? But this is not an interpretation of anything else. It is just, hopefully, theory. I've given you a well-defined space-time structure that will restrict me in specifying the rest of the theory, which is, okay, what is matter made of? And what else is there? And how does it behave? The dynamics should all be specified in terms of the space-time structure I gave you, right? And Fantastic. The matter ontology should be specified in terms of that structure. So I'm very constrained about what I can do, but there's still, any number of possibilities.
Fantastic. Well, that's a great setup for what I have in mind regarding your work. And let's see. Should be able to share. Okay. Can you see the screen?
Yes.
Okay. Because I see it as because of its close connection to two different frameworks. I see it not only as a theory, but a promising theory to respond to some of the biggest open questions, not only in physics, but in other areas of science. So I'd like to walk us through this. And I thought I would start with this slide. You, of course, know what a spherical cow is. Very quickly, for listeners, I want to ask them to look it up. I don't want to spend too much time on this. To look it up, what a spherical cow is. In a sentence, it's a running joke among physicists who use simplified statements and assertions to move science forward. So cows, of course, are not spherical. You see the cows on the screen here. That's not the way cows are. But often physicists make very simplified, sometimes to outsiders, absurd affirmations to simply get the ideas across in a very simple way and to make progress toward a solution to some problem. So spherical cows are going to play an important part of what I'm about to say. I'm going to run through quite a bit of material in a short amount of time. And I'm going to cover the research of at least 8 or 10 world-class research teams. So it's going to be very cartoon-like what I'm going to say, but I think we can have an interesting discussion based on these ideas. So what I'm going to say is I'll divide it into 3 parts, and I think I can cover them in about 20 minutes. Do you have time for that, Professor?
Yep.
Okay. So the first thing I'd like to talk about is the conceptual overlap between discrete geometry, which listeners will have remembered that Professor Maudlin begins his model on the idea of a line, a discrete line that cannot be broken down any further because it's discrete. And this is non-Euclidean because in a Euclidean geometry, the line can still be broken down into points. And this has immediately, those who are familiar with string theory, at least a very basic rudimentary conceptual similarity to string theory, which posits that the most fundamental object in physics is not a point particle, but rather a one-dimensional string that is also discrete. So I want to talk about that. And then I want to also talk about how the connection of discrete geometry and Professor Maudlin's work regarding the nature of time. I think some really interesting and relevant ideas come out of this. And then lastly, what these first 2 points, what they say about the ontology. What are the beables? What is this new picture of nature? What is it telling us about nature? And what does it imply about some of the biggest open problems that we have as humans? Okay, so the background challenges against this whole presentation are going to be quantum gravity, by which I mean our inability to reconcile macroscopic things with microscopic things, or general relativity with quantum mechanics. And also the famous measurement problem. I'll go into a little bit of details what I mean by that. Professor Maudlin obviously knows what that is. So that's going to be the background. So here's part 1. In part 1, like I said earlier, I want to speculate on some of the connections between what Maudlin has described in the first part of this talk to string theory. Okay. Not sure if I can move this. Trying to move my picture on the screen. I don't know if it shows up on the recording. Do you see, Professor,
I see
the
a line.
image?
I see a line. There was a rectangle for a second, and now there's a line. That's all I see.
But for example, myself and yourself, do you see? Is it obstructing the view?
No.
No. Okay. Fantastic.
No, what I see, you're off to the side. I mean.
Okay. Fantastic. Okay. So as Professor Maudlin described, he begins with a discrete line, and from that line, the line is extended, it goes into a quadrilateral, and that quadrilateral, if it's extended, goes into a cube. I'm sorry. What do you refer to this, Professor?
I mean, look, officially it's a quadrilateral. I call it a square, but I'm cheating because, I haven't defined lengths and angles. So,
Okay.
it's really just a quadrilateral. And I guess the other, the other thing is some kind of a quadrilateral based prism or something, but I call it a cube, which is, again, it's cheating a bit because
That's okay. We're being
official
very,
definitions require defining angles, and I haven't defined any angles.
We're at the spherical cow level, so we'll call it a cube. Okay.
Yeah, I think it's easier.
Sure. If you extend the quadrilateral out in 3 dimensions, and then you get a cube. And in a very interesting process that the professor has partly covered today, from this extension of the line into 3 dimensions, what actually emerges is Minkowski space and Euclidean geometry. And this is interesting for many different reasons that we went through some part of them today. But at the level of path connectivity, this is a term that he uses quite a bit. When you include time, Euclidean geometry and Minkowski space emerges from non-Euclidean, just discrete geometry, and you don't get similarities, among other benefits that we're going to talk about now. So this path connectivity approach is reminiscent of Feynman's sum over paths approach to quantum mechanics. So starting from a discrete non-Euclidean geometry, as the professor has already indicated, we arrive to standard quantum theory, and specifically the path integral approach or Lagrangian mechanics that is so absolutely fundamental to the vast majority of physics today. Okay, so string theory has some similarities here. And what string theory posits is that the point particles that we view as represented as waves are not really the fundamental thing in nature, but rather strings and discrete strings that vibrate in more dimensions than we have access to. So they have tiny dimensions, they vibrate. This aspect of strings, to my knowledge, is not mentioned by Professor Maudlin, but the discreteness of the string and the indivisibility of the string certainly is, and that's a notable conceptual overlap. So string theory responds to the problem that I mentioned earlier, that general relativity and quantum mechanics seems to speak different languages, right? But string theory has many problems. Some of them are, we're going to talk about them, is how do we test it? We can't test it. The kinds of energy levels that are needed to test it, we just haven't been able to access them. And then 10 dimensions. What does it mean to say that we live in a world of 10 or a universe of 10 dimensions? Right? That's a big problem. Another problem is the fact that one of the crowning jewels, intellectual and mathematical jewels of string theory, is something known as the ADS-CFT correspondence, more popularly referred to as the holographic principle. So string theory is promising as a mathematical theoretical approach to quantizing gravity and unifying general relativity and quantum mechanics, but it's going back to one of the original ideas that we started with. It doesn't say much about the world as presented to us on the one hand, and how do we make sense of this, and then how do we test it, right? So there's another problem, a big problem with string theory, is the fact that we don't live in an ADS space, an anti-de Sitter space. So all of these problems need to be confronted. And I'm going to argue from here forward that Professor Maudlin's approach to discrete geometry gives us a promising avenue to continue to research. And so several prominent physicists are approaching these various problems with string theory. One of them, very noteworthy, is Eva Silverstein, who's at Stanford, a colleague with Leonard Susskind, who's also one of the superstars in this area. So what she and her colleagues have done for the past quite a while now, what they do is take ADS space, the problem with ADS space, the fact that we don't live with ADS space. They very simplistically, cartoon-like, obviously there's more involved here. They cut the space in half, okay? And they bring it together to make what is called a DS space, a de Sitter space. And many of the top physicists, Kumaran Baffa, Leonard Susskind, Eva Silverstein, and many, many others, believe that this is a much more realistic and promising approach, because although we don't live in a de Sitter space, looks like we do live in a de Sitter space. In other words, the universe is de Sitter. And so in a nutshell, what's being posited here is that you see the DS at the bottom here, the bottom circle sphere. The idea is that the outer boundary of that sphere is a two-dimensional boundary, but there's a duality between that two-dimensional boundary and the three-dimensional space inside of that boundary. So that's holography in a nutshell. Now the interesting parallel here, again, in a spherical cow kind of way, is, and here you see again pictured the de Sitter universe as a Poincare disk. So what you have here is a spherical cow kind of parallel between how a brain is separated into two different hemispheres, and how the outer shell of the brain has access, is two-dimensional, and has access to information that is received from outside of that. And in some sense, there's a copy of everything that goes on in the brain. So there's an interesting parallel here, I would say, between the latest progress that we're making in string theory and some of the latest progress that we're making in the brain sciences. And furthermore, this applies not only to human brains, but as you see on the screen, to many other animal brains as well. So the way that the universe appears to be organized from a string theoretical approach, and I'd like to insert a parenthesis here and remind ourselves that despite some of the bad rap that string theory gets in popular media and even in some scientific circles, string theory today represents the culmination of 500 years of very well-established science. So it really is one of the most promising results or fruits of the scientific revolution. This is not some back alley theory that people are promoting. This really is at the forefront of human knowledge. And so this symmetry, spherical cow kind of symmetry between how information is processed, appears to be processed according to string theory, in a holographic universe, is an interesting parallel between how information is processed, again, in a very well-established way scientifically in animal brains. So on the screen here, you see another a representation of how we see on the left side of the screen, information from the exterior world arrives into or at the brain through the five senses on a two-dimensional level, right? And then from there, it enters into our brain in the interior of the brain, which is 3 dimensions, but it also gives rise to everything we experience as humans, everything that we're conscious of. So in some sense that the 2-dimensional world gives rise to a 3-dimensional world, which is also multidimensional if we count our experience of reality as more than 3 or 4 dimensions. So here's an interesting mathematical point. What you see on the screen is the Hamiltonian of an open-ended relativistic string. And here, the Hamiltonian is intimately connected to the Lagrangian. You just actually just switch the positive sign to a minus sign, and you have the Lagrangian. And Lagrangian here is relevant because it's the path integral approach that we mentioned earlier, which is what Professor Maudlin has arrived through discrete geometry. So the parallel here is interesting and I think noteworthy to continue to reflect on, right? Because the string and the path approach are common to both discrete geometry and string theory. So what's interesting now is that for example, a black hole shares a certain symmetry with a falling apple, a mathematical symmetry, despite the fact that they're very, very different things, right? So in a similar way, what's being proposed is that the universe, through the things that we just talked about, also shares a kind of symmetry, a mathematical symmetry with animal brains. So the way that the cosmos itself seems to be organized and process information and emerge physical reality is very similar to how information appears to be processed in animal brains. So a lot of this is being worked on by some of the superstars in theoretical physics, many of which you see on the screen. Maybe the most noteworthy, in my opinion, is a proposal by Leonard Susskind, who has suggested that creating a shell, very similar to what we've talked about so far here, the ADS-CFT correspondence and holography, is going to be the next big breakthrough in quantum computing. So each one of these persons on the screen has different approaches. Some of them, well, all of them are super interesting, but this is something that's being worked on in the top universities and top research centers around the world. In addition to that, there's a growing convergence from various disciplines, various research groups. For example, from Qubit, amazing advances in artificial intelligence and neuroscience. I don't have time to go into all of those here, but I'll place a list of them in the video description for anybody who's interested. Okay, so let me pass to part 2. I think I'm going a little bit too slow, so I'll pick up the pace here. And I want to talk about part 2 is interpretations of quantum mechanics. And this is something that Professor Maudlin does not like. I understand why he does not like it. And it's if you understand his objection, I think he's absolutely right, because if we're going to talk about understanding the world, it's not just about math. The world is more than math. The formalism is important, making predictions are important, but what we're really after is what is there? What is nature about? No? And the measurement problem, very quickly, is the idea that we don't know how we transition from the probabilities of a wave function on the left to the 100% certainty of the Born rule. This is an outstanding problem in physics today. Some argue it's the most important problem. So as a way to solve this problem, there's at least 16 or 20 different interpretations of what happens here. So we're only going to visit a couple of them just as representative samples. One of them is the many worlds interpretation. According to the many worlds interpretation, every time a quantum measurement is made, the universe actually splits into a potentially infinite number of copies of itself. So according to this, there's another universe where I'm not speaking English, I'm speaking Spanish, and another one where I'm wearing a different color shirt, and ad infinitum. And that's one way to solve the measurement problem. It's mathematically rigorous. Some people claim that it's beautiful, but I can't argue against that, but I will say that it has absolutely nothing meaningful to say about this world, the one that we're actually in, the one where you're listening to me speak English and not another world of infinite other possibilities. Okay, so another one another interpretation is the two-state vector formalism of Yakir Aharonov. And Professor, you've given a couple of talks on Aharonov and his work. Can you quickly tell us about Aharonov
Well, I've talked about the Aharonov-Bohm effect, which is a different matter than this two-state vector formalism. Actually, I was just with Aharonov in Israel last week. The two-state vector formalism, I mean, if I can say a word about it, that mathematically, I do an experiment by preparing a system in a certain way. So there's a preparation. On the basis of the preparation, I ascribe a wave function. That wave function evolves forward in time by Schrodinger's equation or by a collapse equation. In this case, it would just be by Schrodinger's equation. And then, of course, as you know, typically in quantum mechanics, out of that wave function, you don't get a specific prediction of what the outcome of the experiment will be. You get a set of probabilities that are given by Born's rule. Now, one thing you can do is so you can think of the preparation as a pre-selection, right? You're just taking systems and only looking at certain of them with certain features that you've prepared. One thing you can do is do a post-selection. That is, if I run this experiment many times and I get different results, I can then just focus down on the cases where I got a certain specific result. So that's a post-selection. And you can talk about, if you have not just the initial wave function, but this post-selection, then there are various questions you can ask relative to having that information. And in a way, they're well-defined questions you can ask that everybody will agree about. Now, what Aharonov has done is take that general idea and then make it into a very, to me, difficult to understand proposal, which is that think of the post-selection, which we normally think of as just picking out certain particular experiments that came out a certain way. Think of that as a kind of preparation for a second wave function that's going backward in time, right? So you sort of see the symmetry, right? Your initial preparation prepares a forward-going wave function, and then this post-selection somehow prepares a backward-going wave function. And then you get these, that's why it's called the two-state formalism. Both of these evolve by Schrodinger's equation, but at every time you have this pair, which is what you have on the screen here, phi inside. And then there are some proposals about how to extract from the pair a narrative about what's going on in between. Now, I'm not sure I really understand what that narrative is. I'm not sure that there's even agreement among, say, Aharonov and Elitzer, who also uses this. I'm not entirely sure there's even an agreed upon theory. I know that Aharonov is not at all a many worlds person. He's very opposed to many worlds, so you can't think of it that way. I'm not quite sure I understand how he thinks of it. But since I'm somebody who thinks time only goes one direction, I'm of course not very sympathetic to the idea of a backward evolving, right, as it were, backward evolving second wave function. And furthermore, it doesn't seem to me that the activity of post-selection looks like the time reverse of a preparation. So I conceptually, I don't quite understand how this is supposed to fit together.
Okay, well, thank you for the explanation. I'm going to claim very quickly that just as you have derived the forward march of time using discrete geometry, I think we can use the formalism that has been developed by Yakira Haranov to develop the same backward evolving time. And I'm going to explain why this is relevant in the next few slides. So, and maybe it's not worth mentioning, but Yakira Haranov is obviously one of the most accomplished and successful physicists alive. He's very well respected, and his two-state vector formalism has led to any number of different empirical results that are worth mentioning. I put a copy of several papers in the video description. So in addition to Haranov, some other top physicists have toyed with the concept of retrocausality. Among them, Richard Feynman wasn't successful with the idea. Frank Wilczek, more recently, is still working on the concept of axions being a result of a retrocausal physical process. Hugh Price and John Kramer are also working on this concept. So it's not something that's completely, totally isolated to Aharonov and his team. So, but what does it mean? What can we possibly say to mean that a backward evolving wave function has an impact on the present? So what I've told Professor Maudlin the first time around is, in some sense, every one of my sentences is guided by some conception that doesn't exist in the past. It exists in the present, but there's some sense in which that future goal is guiding how the present evolves. So Professor Maudlin likes to speak about the world as it presents itself to us. This is difficult for me to get away from. This is something that we experience as humans, that the future, in terms of goals, sure, we can think of it as, no, it's a goal that I have in the present. Yes, we can think of it that way. But what Aharonov has demonstrated is that we can also think of that, the future, in particular, our goals, although Aharonov doesn't say this, I say this, that our goals and how I decide to act has an impact on how the future evolves. If I decided to get up out of my chair at this moment, the future would in fact evolve in a different way than if I continue to sit here. So why is that? Why is that relevant? It's relevant because some of the major problems that we're facing, not only in physics, but also in many other disciplines, can be resolved if we take this two-time approach. So on the left, you see the many worlds picture where the universe branches out using the same math, the same basic ideas, 500 years of well-developed scientific progress, but it doesn't have anything to say about this world. Whereas if we take the two-time approach, which I should stress is equivalent, it's equally acceptable as an interpretation of what's happening in nature. If we take the two-time approach, we have very interesting tools available to us to respond to some of those biggest challenges that we're facing. So my main idea here is that discrete geometry, what Professor Maudlin is working on, is in some sense equivalent to string theory on the one hand and the two-state vector formalism on the other. Understood this way, and from what the professor has been able to do so far, obviously there's still a lot of work, as he has indicated. There's still a lot of work to be done. But the idea is, from this initial approach, we can develop all of physics using a forward and backward evolving wave function. Again, using the very simple discrete geometry that Professor Maudlin has developed, that doesn't lead to singularities and has any number of other different advantages. So last part. So what's the ontology here? What is this telling us about reality? What is nature like? So it seems to me that here an important point is to remind ourselves what we agreed on at the beginning, that we're going to anchor this in, we're faced with a series of very difficult challenges that are problematic, and one of them being the non-zero risk of potential extinction through nuclear war or through any number of other threats. So Carl Sagan famously said that we are made of star stuff. So one of the conclusions I would offer as food for thought is not only that does this make it appear that we're made of star stuff, but this is actually, I suppose, tautological in some sense. We're obviously star stuff. But what this appears to be telling us is that we see nature we see ourselves being reflected in nature. That seems to be a promising approach. And I'm going to outline why I think it's a promising approach in this last part of the talk. So the claim I'm going to make is that it's scientifically productive, not philosophically, not spiritually, scientifically productive to think of nature as a reflection of ourselves. Okay, so what are the implications? There's deep implications for not only for physics, right? Because if you remember, string theory actually unites physics. And my claim is that the two-state vector formalism resolves the measurement problem. Two of the biggest open questions in physics. But not only that, it has important implications for political theory, for psychology, for artificial intelligence, for philosophy and morality, for brain science, for religion. And these are not just casual claims that I'm throwing out there. Each one of these disciplines has a number of open questions, difficulties, problems, paradoxes, that my claim is that they are resolved by this approach through just discrete geometry and string theory and the two-state vector formalism, to understanding the nature of reality and to solving these very concrete problems that we're having. So in a word, what I'm proposing is that Professor Maudlin is actually working on a theory of everything. This is really practically what he's working on. So as the last couple of slides here, what you see on the screen is just came out on a paper on Archive by several prominent academics. One of them a Fields medalist, who is proposing to establish a wormhole, what he calls a wormhole, a very strange word to use in my opinion. I like to say that it's more of a symmetry that we see in nature at the fundamental level, and open questions or open problems or solutions to some political theory. So what they're doing is establishing a wormhole between quantum theory, a lot of the things we've talked about today, and social choice theory. So I'll leave a link to their paper in the video description. So I offer this to demonstrate how there's a growing convergence along these lines, and Professor Maudlin's work, I think, is a very interesting, much more promising approach, by the way, than what they have proposed in this paper. They have, in my opinion, they have several difficulties, and furthermore, that it's not as extensive or widely applicable as I claim, would be to take a discrete geometry approach. So some of the people that I've talked to on the channel, I've had the privilege of talking to, are on the screen, and their work is completely aligned with everything I've talked about today. One of them is Michael Levin, one of the top biologists in the world, who's working on actually regenerating animal limbs and hopes to apply the technology to humans. And in our talk, we talked about teleophobia. People are afraid, scientists are afraid, and he often gets criticized because he talks about goals and purpose in nature. And they ask him, why do you say that? Why can't you just leave that out and just do the science? He says, no, listen, this is the way I'm doing it. And I need to do this because it affects the way I do the science. Okay, it changes the way I do the science. This is not a philosophical approach. It actually changes the science. Another person that we've talked to in the past is Eliyahu Cohen, who's working on quantum computing. Carl Friston, who's doing very interesting work in neuroscience and the free energy principle, and Vitaly Banchurin, who has proposed a new model of seeing the world as a neural network. All of these are extremely compatible with everything I've just talked about today, and I encourage listeners to take a glance at our discussions or with each one of these, or they're on the channel. So I think this is the second to the last slide, and I'm done. So what I propose here is that discrete geometry, in essence, we've built a structure here built on 500 years of very, very extremely well-established science, and incorporated some of the key concepts such as holography, extra dimensions, entanglement we didn't talk about, but it's relevant, it's important, and uncertainty. We've used string theory and the two-time picture of Aharonov to show how discrete geometry can sit up on the top of this structure and get us to the point where a more promising approach to quantum gravity. That's the claim. It's an extraordinary claim, but I think there's extraordinary evidence to back it up. So that's it. I suppose I'll close here, and hopefully you have time to talk about this a little bit, Professor.
Yeah. So I guess I'm gonna put on my professor of philosophy hat for a minute.
Okay.
And be something, unfortunately, of a professional wet blanket to some of this, because that's kind of my job. So let me. There are some things you said, and I just that I want to go into in a little bit of detail. So just to list them out to make sure if I forget, I want to say a little bit about string theory. I want to say a little about holography, direction of time, and teleology, and a bit about neuroscience. Okay, so I understand why, because I have these discrete one-dimensional geometrical units in my geometry, and just as I've got points, and you could postulate point particles in this space-time that would just move from point to point and have a continuous trajectory. It's a very natural thing to do. You could also postulate fundamental atomic one-dimensional elements, these lines, and they would move. Or two-dimensional elements, these surfaces, or three-dimensional elements. So these are natural thoughts that would occur to one. But my atomic one-dimensional things can't do what strings do. They can't vibrate. I mean, that is the picture one's often given in string theory is that these strings are wiggling. And the only way a string can vibrate or wiggle is that it has all these intermediate points that are moving. They're moving relative to each other in certain ways. I mean, it has to remain a continuous line, but all of that vibrational motion would not be available for my one-dimensional discrete things, because literally they don't have interior points that can move. One thing they can do, which I'll just mention, is they can spin. That is, if you imagine on my grid, I have a one-dimensional thing. At one moment, it could be like this, and the next moment oriented like this, and then oriented like this. So the notion of having a spin to it, which is relevant for quantum theory and standard model, you have objects with spin, that you can imagine doing, or even a two-dimensional element being oriented like this, right? Then like this. I mean, there are various kinds of spin-like motions you could give them, but vibration is not among them. The other thing about string theory is that one of the motivations for string theory that Ed Witten often talks about, and I understand it, it only arises because string theory is done in a continuum. So he would look at a standard Feynman diagram of, say, two interacting electrons. And there you would, again, think of the electrons as point particles. They're moving along, and maybe people have seen these diagrams. You would have these two electrons, and then you put a photon, which is a wiggly line, this way, and then they move apart, right? So you sort of think of, oh, the repulsion of these electrons is mediated by a virtual photon going between them. And what Witten pointed out, which is mathematically correct, is that in that picture, which is in a continuum, you need two very different kinds of dynamics or propagators. You have a propagator for the straight line, the free propagator, and then where the interaction occurs, which is at a very specific point where the electron, say, and the photon come together, then you put an interaction, and then you freely propagate. So it's free propagation, interaction, free. And what Witten said is if I replace these point particles with strings, like closed strings, like loops, and I draw this same Feynman diagram, I can do it where it's smooth everywhere, right? It is in space-time a completely smooth structure. And so you would have the same propagator everywhere. And this would simplify the theory and much more deeply constrain the theory, because in the standard theory, the free propagator doesn't really constrain the interaction. But the idea is this is going to be a much more constrained theory. Now that makes perfect sense in a continuum. It doesn't really make much sense in a discrete structure, okay? So that motivation for string theory is a bit undercut if you think space-time is fundamentally discrete. So I wanted to talk about that. The second thing I wanted to talk about was the holographic hypothesis. The holographic hypothesis, or proposal, whatever you want to call it, is that the physics in a bulk, in a volume, is in some sense isomorphic to a different physics that's defined completely on the surface. So one dimension smaller. So if you think of a sphere, the volume of the sphere is three-dimensional, the surface of the sphere is two-dimensional. Somehow the holographic hypothesis says that everything going on in the interior of the sphere, its physics maps to physics that can be defined just on the surface. Yeah. Now, from that, they sometimes make an odd move, and they sort of say, well, really what that shows is that only the surface is real and the interior doesn't exist, which doesn't really make a lot of sense, because you could equally well say only the interior exists and the surface doesn't exist, or you could say they both exist and they just happen to be related to each other. Anyway, I mean, I myself don't see much plausibility in any of this, but let me leave that aside. In terms of the connection to neurophysics, I just want to point out, I'm not quite sure what you had in mind, but brains aren't like that, in that the neural processing on the surface of my cortex certainly does not replicate to the neural processing throughout my brain. I mean, I can't go and scoop out the entire interior of your brain and expect that just the cortex is going to behave, I mean, that's just not how, that's just not how it works. So the analogy, and I understand from the picture, you have this kind of this bilaterally symmetric picture of these two things glued together, and you've got these bilaterally symmetric brains in primates and so on, who tend to be just bilaterally symmetric all in all. But I'm not sure how one could argue for a symmetry, the kind of thing that is postulated in the holographic hypothesis. It would sort of say, gee, all my thinking is going on literally in my skull, right? In my cranium, in the things surrounding my brain. And that, that's not what's going on. The other thing, I guess, I mean, about time, again, and this maybe wasn't what you were hoping for, but time, a single direction of time is just built into the structure I postulate. So doing retrocausation in anything like the structure I'm working with doesn't make sense, because I really need time to be just one directional. The idea of retrocausation, which, as you say, various physicists have worked on, Feynman and Wheeler worked on, and Kramer and so on, that somehow the future state can influence the present state, just as we think the past state can influence the present state. All right, so that's a proposal. You need to work out a lot of mathematical detail. It is different than saying what I do depends on my goals. And I just want to say, for a very simple reason, when I say my present activities, what I'm doing, talking to you now, depends upon my goals, what I hope to have happen, the future I would like there to be, which is true, is a very different thing than saying it depends on what the future actually will be, in the following very simple way. If you look back over the past few days, you can get a good explanation for why I'm saying the things I do from what's going on in my head. Suppose, as unfortunately could happen, I get hit by a bus tonight. Okay, so my future, I don't finish writing the book I'm hoping to finish. None of this happens. It just, the goals never actually materialize. It would be very strange to think that that has any present effect on my behavior. That would suggest that by carefully analyzing, this present conversation, you would get indications or glimmerings that I'm going to get hit by a bus, because that's going to wipe out all of these future goals, right? They won't actually exist. And so if the idea of retrocausation is that the actual future influences the present, you do get this puzzle, which is that, gee, sometimes things that are really big physical events in the actual future, like a thunderstorm or a flood or something that people, or the asteroid hitting the Earth, that have a huge effect on the future, but there really isn't marks of it or indications of it beforehand. There's all kinds of marks of it afterwards, but there's no indication of it beforehand. So I think the way that our behavior is governed by our goals and our intentions and our desires and our anticipations and our internal mental model of the world, all of that is very interesting and an interesting thing to study, but that's a different thing than positing retrocausation, which would have a very different kind of structure. And the last thing I'm going to say, and I'm just going to repeat to you a conversation I had with a colleague of mine, Renee Weber. And Renee was very interested in physics and science generally, but she was not trained as a physicist or scientist. And actually, she was very interested in mysticism. And she through some mystics got connected to David Bohm and then got connected to John Bell and Hawking. And she wrote a book called Dialogues with Scientists and Sages, which I think actually you would like, because there's this trying to bring together, mystical traditions and scientific speculations in a certain kind of interesting way. And Renee used to try to draw analogs between physics and ethics. And she was very happy about quantum mechanics because it has this kind of global interconnectedness in the physics. And she would say, but that's great because, ethically, as the Buddhists would say, we're all interconnected. We should care about all conscious beings, right? And so she would see these analogs between the physical postulates and certain ethical principles. And I just said to her one day, I said, look, but Renee, you really wouldn't want to say that if Newton had been right and quantum mechanics, just the world was not quantum mechanical, it was all Newtonian physics, that it's okay to kill each other, would you? And she said, no, I wouldn't, I wouldn't want to say that. And so you see, you don't, you really take a risk if you try to tie physics together with ethics or political theory or whatever, because you don't want to say that a certain discovery in physics that might come up next year could undercut all of your ethical obligations, could undercut everything you think that is important in the world, and how you should treat other people, and how you should care about the environment, and how you should, work hard to avoid nuclear war, all these things that are so important to you. You really don't want to think that some new discovery in physics could undercut all that. So these analogs are a bit dangerous. I mean, I understand why they're attractive. But I think if you propose them too seriously, you're going out on a limb you don't want to be out on. And you want to say, no, we should care about the environment no matter how physics comes out. We should try to avoid nuclear war no matter how physics comes out, right? And although there's always, an attraction to seeing these kind of metaphors or analogies, if you try to make the connection too tight, you're putting things even at risk you absolutely don't want to. So I guess that's,
Yeah, that makes sense. That makes absolute sense. I will say in response to the last point that there's nothing being posited or trying to be established here between how physics could turn out. It's actually how physics is, demonstrably so, empirically, as far as we know today. So I understand your point about, okay, not tying physics to how physics could turn out to ethics if it would then have negative implications. Obviously not. What's being posited here is a connection between the physics and the math that's already well established to ethical systems or political systems. But not because that connection is made does it guarantee that political systems or ethical systems are going to be or we're going to have positive outcomes that we're looking for, because the physics would indicate depends on what you do.
Sure.
Depends on, absolutely, but
absolutely depends on what you do. Absolutely.
Yeah, absolutely depends on what you do. Sure, but we can study the physics to understand, okay, when we do this or this, there's going to be different outcomes, and resolve some of the tension, some of the, this is not speculation. This is real, real solutions that are being proposed to open questions in other disciplines. For example, Arrow's impossibility theorem. Whale and his group, and also myself, have worked on solutions that come from physics to propose solutions to those problems. So it's not like speculation, it's not mysticism. This is, as far as I'm concerned, hardcore physics being tied to real open questions in other social sciences. In any case, I appreciate the feedback. I think your points are valid. We could probably go on all day and all night. And
sure we could.
We should.
And again, I know it's not, but this is just what I do.
No, that's fantastic.
And I'm sure we could continue the conversation indefinitely, but I think people have quite a lot to chew on from this.
Yes.
If they've stuck around this far, they have already quite enough to think about without going on any further into it.
You've been extremely generous again, Professor. Thank you so much for your time. What kind of things are you working on now, apart from your second book on geometry?
That's the main thing.
That's
I've
the
just
main
been
project.
a little bit
Okay.
obsessed with trying to do some calculations for a while. I mean, there's another thing I'm involved in, but tangentially and not centrally, which is, I'll just mention it, of interest, which is that there's some work being done on physics on arrival times in physics. So if you send out particles at a screen down a waveguide toward a screen, you can use quantum mechanics in an obvious way to make predictions about where it'll hit the screen, but it's not quite so obvious even how to use quantum mechanics to predict when they'll hit the screen, what the arrival time distribution will be if I do this many times. And there's work being done by Siddhant Das, which on this, which to me is amazingly promising toward giving us the possibility of some laboratory experiments that could give us data which might really provide a way forward to test various approaches to understanding quantum mechanics. And to my knowledge, nobody's looked at this carefully. And it's a very interesting thing to think about. And there's a lot of conceptual issues and technical issues that have to be resolved. But anyway, this is, again, and this is not centrally work I'm doing, but I am involved in discussions around it. And I think it's something people might have on their radar screens that could become something quite important.
Okay, I'll take a look at that. I'll leave a link in the video description as well to this work. Professor, thanks again for your time. Have a great rest of the day, and I look forward to keeping track of your work.
Okay, thank you.
Okay, take care.
To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.